In healthcare, uncertainty is just everywhere. A doctor can never be 100% sure about a diagnosis or if a treatment's really going to work. But what if you could actually measure that uncertainty? Well, that's exactly what we're talking about today. We're diving into probability, this amazing tool that helps us turn all that doubt into real, data-driven insight. So think about this for a second. When a doctor tells you a new drug is the way to go, or when you hear about a new public health screening program, how do they know it's the right call? I mean, they can't be 100% certain, right? They're working with incomplete information always. The answer to how they make those huge decisions, how they weigh all the risks and benefits, well, it all comes down to the science of probability.
All right, so here's what we're going to cover. First, we'll get a handle on what probability actually is. Then we'll learn some of the basic lingo. After that, we'll get into calculating some odds, see how that uncovers some really cool patterns, and we'll wrap it all up with maybe the most important pattern in all of medicine, the famous bell curve.
Okay, let's jump right in. Look, probability is way more than just flipping coins or rolling dice. It's really the fundamental way that medicine and public health deal with uncertainty. And let's be real, uncertainty is unavoidable. It's all about making the best possible call with the information you've got. So at its heart, probability is just a number between 0 and 1. That's it. If something is a probability of 0, it's impossible. It's never going to happen. If it's 1, it's a sure thing. It's certain. And pretty much everything else in life, especially in medicine, like the chance of a drug having side effects or a surgery being successful, falls somewhere in between. This simple little scale is what lets scientists actually put a number on risk and compare things. Okay, to really get a handle on this, we've got to learn the lingo. Probability has its own vocabulary, Just a few key terms that are the building blocks for everything else. So let's run through them real quick. First up, we have the event. Now, this sounds super simple, but trust me, it's crucial. An event is just any specific outcome that we care about and want to measure. So a patient testing positive for malaria, that's an event. A person recovering from a sickness, also an event. Once you define the event clearly, you can actually start to measure how likely it is to happen. All right, so for any event, there's something called the sample space. This is just a list of every single possible thing that could happen. It's pretty straightforward. So if our event is that malaria test, what's the sample space? Well, the result can only be positive or negative. That's the entire list. That's your sample space. Okay, next up, mutually exclusive events. It's kind of a fancy term, but it just means two things that can't possibly happen at the same time, right? A person can't be both biologically male and female. A lab test can't come back both positive and negative. It's one or the other. Knowing this is super important for getting our calculations right because one outcome automatically rules out the other. Now, this is where it gets really interesting. We've got independent versus dependent events. So two events are independent if one has absolutely no effect on the other. Like the result of your malaria test has nothing to do with the gender of a baby being born across town. But in healthcare, what we're really interested in are the dependent events, where one thing does affect the other. A classic example, engaging in unprotected sex directly changes, it increases the probability of contracting HIV. Finding these connections, these dependencies, is how we identify risk factors for diseases. All right, so we've got the lingo down. Let's see how we can actually use it. With these basic ideas, we can start to calculate the real odds of some pretty complex health situations. And this, right here, is where probability stops being just theory and becomes a seriously powerful predictive tool. Let's take a look at a really common question you'd hear in a clinic. We know that things like high blood pressure and diabetes often go together, right? So here's the puzzle. What's the probability that a patient has diabetes if we already know they have hypertension? This is what we call conditional probability. Okay, to figure this out, let's look at some data from a group of 100 patients. This table shows us who has diabetes, who has hypertension, and who has both. Now, the key here is to notice that out of all 100 people, a total of 25 have hypertension. So for our question, that's our entire world right now. We're only going to look at that specific group. So forget about everyone else for a second. We're zooming in on just those 25 patients with hypertension. Now, look at the table. Of those 25 people, how many also have diabetes? It's 15. So you just do the math, 15 out of 25. That gives you 0.6 or 60%. And boom, just like that, you see how knowing one thing, that someone has high blood pressure, can totally change the odds of them having something else. It's powerful stuff. Okay, calculating one-off probabilities like that is super useful. But the real magic happens when we zoom out, way out. Instead of one patient, think about thousands or even millions. When you start plotting all that data for a whole population, these incredible, predictable shapes and patterns start to show up. And these patterns have a name. They're called probability distributions. So there are a few different types of these patterns that are really common in health research. You've got the binomial distribution. That's for things with only two outcomes, like in a vaccine trial where you're either protected or not protected. Then there's the Poisson, which is great for tracking rare events over time, like the number of new TB cases in a district each week. But the big one, the one we're really going to dig into, is the normal distribution. This one pops up for things you can measure on a continuous scale, like height, weight, or blood pressure. And that brings us to the superstar, the rock star of biostatistics, the normal distribution. You probably know it by its more famous name, the bell curve. And this shape, man, it shows up everywhere in biology and medicine. It's incredibly important. Just imagine you measure the birth weight of thousands and thousands of babies. What do you think you'd find? Well, most of them would be clustered right around some average weight, and you'd have fewer and fewer babies who are extremely light or extremely heavy. So when you plot all of that on a graph, you get this perfect, iconic, symmetrical bell shape. What's amazing about this curve is how predictable it is. It follows this really neat rule. So first you need this idea called standard deviation. Just think of it as a standard step, or a unit of measurement for how spread out everything is. Okay? So for anything that follows this bell curve, about 68% of all the values will fall within one of those steps from the average. So for our babies, it means the vast majority have a birth weight that's pretty close to the average. Okay, now let's take two of those steps away from the average in either direction. Suddenly, you've captured about 95% of the entire population. And this 95% number is huge in medicine. Why? Because it's often how doctors define the normal range for things like blood tests. If your result falls outside that 95% range, it's considered an outlier, something a little unusual that might need a second look. And finally, if you go out 3 steps, 3 standard deviations, you've basically got everybody, 99.7% of the population. So getting a result that far away from the average is incredibly rare. This whole predictable pattern, the 68, 95, 99.7 rule, is exactly what makes the bell curve such a reliable and powerful tool for doctors and researchers. So why do we care so much about this one shape? Well, think about it. It lets us define what's normal. It helps us spot results that are unusual. It's the entire foundation for the statistical tests that tell us if a new drug is actually working or not. It literally takes a massive, chaotic sea of data points and turns it into a predictable, understandable system that helps guide life or death decisions every single day. And that all leads us to one final, really powerful question. We've seen how probability helps us make sense of what's happening right now. But what about the future? As we get more and more data, as our tools get even better, the real game changer is prediction. So if we can map out the odds of a disease with this kind of accuracy, you have to wonder, how close are we to a future where we can use all this data not just to treat sickness, but to actually prevent it before it even starts?